Right before test 2, we learned a little bit about vectors. Now we're going to go back and have fun with vectors. So first we're going to learn vector arithmetic, adding, and scalar multiplication, and then we'll do some application problems with them. So, the sum of two vectors is another vector. U plus V. It's called the resultant vector. Subtraction is U plus the opposite of V, and the opposite of V is the same thing except the initial and terminal points trade roles. This is an illustration of what they look like, but luckily it's really easy because all you have to do is add the horizontal components and add the vertical components. So graphically, you draw U, and then the terminal point of U is the initial point of V, or the terminal point of U is the initial point of negative V. Here they are as parallelograms. If you draw U and V, then the resultant goes from one corner to the other. If you draw U and then negative V, the resultant comes from the corner if you drew a parallel. But the important thing for you to remember is add the x coordinates, horizontal components, add the vertical components. So let's do one. We have U is equal to 3, negative 2, and V is equal to negative 1, 4. U plus V is equal to 3 plus negative 1, negative 2, plus 4. So 2, 2. U minus V is equal to U plus the negative of V. So instead of negative 1, let me go ahead and write down what I was going to do. Minus V. There we go. So U is 3 minus negative 1, so plus 1, and negative 2 minus 4. And that gives me 4, negative 6, and there should not be a comma there. I was adding them together. So there's the pretty picture. 2, 2, 4, 6, and there's the graph of it. Scalar multiplication, you start with a number multiplied by a vector, and that number is just called a scalar. You just multiply each term. So it can make the vector grow or get shorter. If it's negative, it switches it directions. So another example, 2. We have V is the vector 3, 1. Then 3V is equal to 3 times 3, 1, which is 9, 3. So 3, 1. I'll do a tiny little graph here. 1, 2, 3, 1. Looks something like that. 9, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3. Looks the same, except it's 3 times as long. 1/2 V would be 1/2 times 3, 1. So it would be 3 halves 1/2. So it would be as if we took this one and went half as far. And then the last one is negative v, which is the same as -1 times 3. 1, which would be -3. -1, 1, 2, 3, 1. It looks something like that. There we go. So, your turn. We'll give you U, V, and W, and notice W's in kind of a different format, and see what you can do with these. We'll come back and compare answers. Did you make it through that one? Oh, let me get my PowerPoint back where it should be. There we are, practicing vector arithmetic. So we had U was 1, 5, V was -2, 3, and I went ahead and wrote W as 4 minus 1. So in order to do our order of operations, first thing I need to do for part A is V minus W. So I did that over here. And I did V plus the negative of W. So the things in W switched signs. So, well, actually I just did the arithmetic here for V minus W, and then here was plus U, and I saved that for the end. But when I did V plus W, I got -6 minus 2, just like when I sketched it. Then I did U and added negative V minus W to it. There we go. And I end up at -5, 3, which is exactly where I end up here when I sketch it. For part B, it's just 4 times V plus 2 times U. So 4 times V plus 2 times U. 4V, 2U. It said I should end up 1, 2, 3, 4, 5, 6 to the left, down 2. And I say -6 minus 2. Next was easy. We just had minus. We needed to half V because we wanted the same direction. And then part D, we wanted twice the length and the opposite direction, so we multiplied by -2. I went ahead and did example 3. But vector components, we learned this last time. Horizontal component is the magnitude times cosine of theta, and the vertical component is the magnitude times sine of theta. And if we need to know what theta is, it's the arctan of y over x, and the magnitude is the square root of the x-coordinate squared plus the y-coordinate squared. So, write a vector with length 7 at an angle 135 degrees to the x-axis. So, 7 is the length, angle is, and yeah, I changed the example. We no longer need pounds here because they're not pounds. We have 7 cosine of 135 and 7 sine of 135. And there's the pretty picture. Okay. Example number 4. We want to find the vector with length 7. That was 3. Find the magnitude and direction of the resultant vector U plus V. So, let me get another sheet of paper and we'll add U and V. Example 4. I'm not going to rewrite U and V. I'm just going to write U plus V equals, I'll give myself some pointy brackets, 6 minus 3, or 6 plus -3, and minus 10 plus 11. And that would be 6 minus 3 is 3, minus 10 plus 11 is 1. I need the magnitude, so the magnitude of 3 1 is the square root of 3 squared plus 1 squared, so square root of 10. To find theta, I look at the arctan of the vertical component divided by the horizontal component. Oh, look, I just happen to have it already punched in. Inverse tangent of 1/3, 18.43. And it's in the first quadrant, so that's the correct answer. Remember, we have to be careful with the quadrants there when we're coming up with direction. So, practice number 2, try this one, and we'll come back and compare. Be careful with the direction. So, first I had to find my vectors, because this time I was given ordered pairs, points that I needed to play connect the dots with. And remember, to find the vector from t to x, you do the horizontal x minus the horizontal of t, the vertical of x minus the vertical of t. So I ended up with 10 minus 3 and 1 negative 11. Then I added those together. I just add the horizontal and vertical components. Found the magnitude, square root of the squares of the components. Then I looked at the inverse tangent. I ended up with a negative number. Well, we want a direction between 0 and 360 degrees. I knew that this was in quadrant number 4 because I would move to the right and then down. So quadrant number 4. So I just took the answer I got and added it to 360 degrees. Now we're going to get a little more application oriented. We have an object launched with an initial velocity of 200 meters per second at an angle of 30 degrees. Find the initial horizontal and vertical velocity components. I left that out. So we're going to find the vector that represents the horizontal and vertical velocity components. And it's straightforward. It's exactly what you expect it to be. X would be equal to 200 times cosine of 30 degrees, which is 200, and I know cosine of 30 degrees is square root of 3 over 2, so 100 times the square root of 3. And since I really don't have that on my speedometer, I'm going to look at 100 square root of, that's not what I meant 100 square root of 3 is about 173.21 meters per second. And then y is 200 times sine of 30 degrees, which is even easier because it's 200 times a half. Equals 100 meters per second. So, pretty answers. Okay, now we're going to have some real fun ones. Kind of like the applications we did with laws of sines and cosines, except now we'll use vectors. Some of the problems can be done either way. An airplane is heading south at an airspeed of 450 kilometers per hour, but there is a wind blowing southwest at 70 kilometers per hour. What is the velocity vector of the airplane's heading, not including the wind? What is the velocity vector of the wind? What is the velocity vector of the airplane's true path? So the sum of the airplane and the wind. What is the true speed of the airplane? That would be the magnitude of that sum. The true direction of the airplane, the direction of that sum vector. and we'll figure out how many degrees off course the plane will end up flying. So, example 6. We have, they're heading south at an airspeed of 150 kilometers per hour. So, where's my straight edge? Draw myself south. Make myself some set of axes, just so I can keep up with what my angles are. Directly south. That's easy. That means this is 3 pi over 2. So theta is equal to 3 pi over 2, or 270 degrees. So for part A, we have the airplane's heading. So I'm going to call it V sub A for airplane. Equals 450 kilometers per hour times cosine of 270. 450 kilometers per hour times sine of 270. Cosine 0, sine -1. The velocity vector of the wind. There is a wind blowing southwest. So southwest means 45 degrees in the southwest direction. So south is down, west is to the left. So this one is 45 degrees past 180, so 225 degrees. So V for the wind is equal to 70 kilometers per hour times cosine of 225. 70 times sine of 225. Well, this is quadrant number 3. Everybody's negative in quadrant number 3, so negative square root of 2 over 2, and 70 times negative square root of 2 over 2, which is negative 35 times the square root of 2, negative 35 times the square root of 2. Now let me see if I did. I estimated, rounded to negative 49.5. So let's do that. Because we're talking application problems, and we usually use decimal approximations, not exact answers. Now we want the true velocity. So we just add these together. So 0 plus negative 49.5. And negative 450 plus negative 49.5 is negative 499.5. Yay, I got it right. And these are all kilometers per hour. Kilometers per hour and kilometers per hour. Okay, let's see what question D was. What is the true speed of the airplane? So D is, and we'll call this one true velocity, V sub t. V sub t is the square root of 49.5 squared plus negative 499.5 squared. That's a job for a calculator. Thank goodness we get one on this test. Second square root. And it's going to be positive, so 49.5 squared plus 499.5 squared equals 501.95. Kilometers per hour. What is the true direction of the airplane? So we want to look at inverse tangent of negative 499.5 divided by negative 4.95. Inverse tangent. I have a negative over a negative, so I'm just going to put in 499.5 over 49.5, and that gives me 84.34. Well, 84.34 degrees lives in quadrant number 1. My airplane is not pointing in quadrant number 1. My airplane is pointing in quadrant number 3. So instead of being 84 bigger than 0, I need to be 84 past 180. So I will take this number and add pi or 180 to it and get 264.34. How far off course are they flying? Well, they should be flying at 270 degrees. So we do 270 minus second answer, and they are 5.66 degrees off course. And 5.66. See what the pretty answers have to say. 5.7. Of course, to the west. So, oh, and you could write this, let's see, 264.3. You could also write that as south 5.7 degrees west. Just like we figured out here, this is south, and then they're going 5.7 degrees west as a bearing, like we talked about back in the last unit. Okay, here's some practice problems. So start with part A. We have a airplane heading north at an airspeed of 600 kilometers per hour and the wind blowing from southwest. You're going to do the same thing. How many degrees off course will the plane end up flying, and what is the plane's speed relative to the ground? So you're going to have to go through all of these steps in order to complete this practice problem. Now, I should have warned you to read this one carefully. This one says the wind is blowing from the southwest. This one said there is a wind blowing southwest. So blowing southwest means it's going westerly and southerly, but from the southwest means it's going from the southwest northeasterly. So the plane's going 90 degrees and the wind is blowing at 45 degrees because it's going from the southwest to the northeast. So speed, cosine 90, 600 sine 90, 80 cosine of 45, 80 sine of 45. Decimal approximation, add them together. Magnitude, 659 kilometers per hour. And then I took my inverse tangent of the vertical coordinate over the horizontal component, and I got 85.07 degrees. But since it should be going at 90 degrees, it is 4.93 degrees off course. Okay, let's try this one. An airplane heads due north again, but there is a wind blowing again from the southwest. This time the air speed is 550 to end up flying due north. How many degrees west of north will the pilot need to fly the plane? A little bit harder question. See if you can figure out how to make that plane go due north. Okay, so I had to go through all of the steps, almost all of the steps, to figure it out. So we got our wind vector. I just named it alpha for the angle of the plane. And it was 550 cosine alpha, 550 sine alpha. And then the true velocity would be the sum of the two. I need inverse tangent of y over x, of my true velocity components, to be undefined because I want it going straight up and it's sine over cosine, so I need cosine to be equal to 0. So I set the horizontal component to 0. I did inverse cosine of negative 42 over 550. So it needs to be going at an angle of 94.42 degrees, which is 4.42 degrees west of north. Let's see what's next. Oh, we have a person leaving home and walking 5 miles west, 4 miles southwest, 6 miles south, 2 miles southeast, and then 3 miles east. How many miles has the person walked so far? If they wanted to walk straight home, how far would they have to walk? If the person wants to walk straight home, in what direction would they have to walk? Okay, so I need a picture. And I'm going to have to kind of put it in the middle because they're going all over the place. Let's see. They walk 5 miles west. So let's make 5 miles west. That would be this direction. They go 6 miles south. They go 2 miles southeast. Not to scale. And then they go 3 miles east. How many miles have they walked so far? Well, that's easy. 5 plus 4 plus 6 plus 2 plus 3. This is example 7. So 5 plus... Oh, I left out the 4 miles southwest. So I'll fix it and come back. Okay, fixed my picture. I added in the little southwest portion, and then I added arrows to make them look like vectors. If the person wants to walk straight home, how far would the person have to walk? So what I need to do is get this person straight home. I need to add up all of these vectors to see where they are. So if I make a vector for each of these little vectors I've drawn, I add them together, I'll end up right here. This is where they are now. So there they are. If they want to walk home, I just have to reverse it and send them straight home. send them back where they came. Because when I add them all together, I'll get the vector that points from their original location to this end point. If they want to go home, I just have to reverse it. So 5 miles, this first direction, I'll put a little set of axes right here, is 180 degrees. So they went 5 miles, cosine 180, 5 sine 180. I think I'll just write down all of the legs first and then I'll add them together. Then here is 225. So 4, they only went 4 miles in that direction. 4 cosine 225. 4 sine of 225. 270. So 6 cosine 270 degrees, 6 sine of 270 degrees. Then they went 2 miles, and this is 45 degrees past 270. So 45 plus 270 cosine 315 degrees to sine of 315 degrees, and then here they're all the way back around, so this is 3 cosine 0, 3 sine 0. And then I'm just going to add all of these things together. I'm going to take a minute and do some plugging and chugging because you don't need to watch me do that. Yeah, I went ahead and did all the arithmetic. So I plugged in the cosines and sines, and then I added them all together, and then I replaced them with the decimal approximations. I switched the signs because they are actually have moved in the third quadrant from their home, so they're going to have to move towards the positive first quadrant in order to go home, and they've got 10 miles to go. So hopefully they have really good shoes on, or they have a phone they can call an Uber. If the person wants to walk straight home, in what direction would they have to walk? So I really don't want to do a whole new sheet of paper for this. Let's see if I can get this part C here. Let's look at the inverse tangent of 10.243 over 3.414. And here's the calculator. Inverse tangent, 10.243 over 3.414 gives me 71.56 degrees. So they need to travel, depends on how you want to say it, 71.56 degrees north, or you could say 90 minus second answer. North 18.43 degrees east. Let's see how I have the answer written here. Okay, I have 71.6 or 18.4 degrees north, 18.4 degrees west. Let's see, I do believe we have a couple of practice problems for you. So try these and we will come back and compare and contrast. This one was way easier than the example because we only had 2 legs to our journey. We went 6 miles north and then 2 miles northeast, how far from the marina is the boat. So north is cosine 90, sine 90, 0, 6. Northeast is 45 degrees, so square root of 2 over 2 times 2. 1.41 is a decimal approximation. I added them together. I squared, took the square root, got the distance, so this is miles. And then I got the direction by doing the inverse tangent. So if they want to go home, of course, they have to reverse their vector and go minus 1.41 and minus 61.41 because they're up here and they need to travel in that direction to get home. So they need to travel. Oh, I did this wrong because I just did as if they were going up here. So I need to fix this. They don't need to travel north. They need to travel southwest. So instead of being 88.26 degrees, let me see, yeah, 88.68 degrees, they need to be 88.68 degrees below the axis. So I need to add 180 degrees to that. Oops, got 2 plus signs there. So, nope. Let's go back and do it again. I have inverse tangent of 61.41 divided by 1.41 gave me that, plus 180. So they need to travel in the direction 268.68 degrees, or I could do that number, 268.68 minus 270 would give me 1.32 degrees, so south 1.2 degrees west. Almost messed that one up there. Okay. Let's look at part B, give that a try, and then we'll see if I can get that one correct. Okay, my picture was pretty bad on this one, but I made it work. It ended up in the middle of the page because I thought they were going to go further north. But they went 3 miles north, then they headed southwest, then they headed northeast. So 3 cosine of 160 degrees, because that would be 20 miles north of west. West is 180, 20 degrees north of it. And then 5 miles, 10 degrees west of south. So south is 270, 10 degrees west of it would be 260 degrees. And then they went north, 15 degrees north of east, which is just 15 degrees because east is 0. So I added all those things up, and they are a little over, well, almost 3 miles from home. Not as bad as the other person. Then I did inverse tangent of the vertical component divided by the horizontal component. I got minus 86.59 degrees, which is in quadrant 3, but they don't need to move towards quadrant 3. They need to move towards quadrant number 2 because they have ended up east and south of their starting point. So they need to move west and north. So I added 180 to it and got 93.41 degrees, or north and then 3.41 degrees west of north. Okay, you got lots of lab manual problems to practice. You can do this.